guess people are here for the lab then. I guess I can start. Welcome, welcome. This is my 384 lab professor submission, and today we're going to be learning about shift registers, namely the 74HC 164. So in this lab, we're going to be recreating some RGB fan LEDs from Corsair. So take a look and you'll see kind of what's going on there. So how are we going to do that? Well, firstly, we're going to use a 7-segment display in a very unique way, one way we haven't done in previous labs. Although I have done my best to make this an extension from Lab 6 and 7 as it's familiar to students. The theory behind this lab is that given a 7-segment display and a push register or a shift register, you should be able to output various symbols, animations, based on given conditions. Now, we're obviously limited by the equipment we have, but if you had, for instance, a Nucleo 64 board or other Arduinos, you could, in theory, encode a series of information. For instance, if I wanted to display the letter A, I could use a shift register to send one line in to create the shift register's symbols, or to propagate, for instance, the 7-segment display with the values needed to make that symbol appear. So later I'm going to ask students to show me examples of this. One example would be to create something that could output status codes. Of course, again, this would require hardware that we don't have in 384. So instead we're going to do something we can do using clocks and our USB test equipment. So to start, students will follow a schematic to build this type of circuit. You'll see that mine crisscrosses a bit. I apologize. I've designed the schematic to work a lot more efficiently than as it is right now. But the only difference is that these crisscross and yours won't have to as much. Simply put, we have voltage, 3.3 volts from our power supply going into our VCC, as well as a reset pin. The reset pin could be given a button, but for now, for this lab, we'll simply send it the information to tell it that it won't reset. So if you send logical 1 to the pin, it won't reset. If it gets a 0, it'll reset it. On the left, yellow cables consist of A through D. A through D, and then cables A, B, C, D, E, and F. We're going to skip G and H. G and H won't be used in this lab, although, again, the push register, the shift register technically will shift up to the output G and H. Using 270 ohm resistors, we then will push or put our outputs into our display. So we have, I'll wiggle them as best I can. We have A at pin 10, B at 9, C at 8, and we have D at 5, E and F at pins 1 and 2, which you'll see more clearly in the schematic. So let's get scopy going. S-copy, as my as Dave would not like to hear. Let's get S-copy going. So we'll just connect our USB headers. And given the INE file with this lab, you should have A0, A1, and A2 already set with the required settings to perform this. So once you've finished creating your circuit, make sure that the power supply is plugged in and the USB is plugged in, and that the D0, D1, and D2 are all hooked onto the board as shown in this schematic. So D0 should go into pin A, which is pin 1 on the chip, and D1 DIO1 should go into pin B, and DIO3 will be our clock, which is the last pin on the left, pin 7. Oh no, sorry, ground is pin 7 on the left. Last pin, pin 7 on the right. Again, refer to your schematic for specific guidance there, but you should be able to see. Here is our clock, right here. And then on the left we have our DIO1 and DIO2 feeding into pins 1 and 2. So, exploring our setup, we are currently sending simply a 1 through A0, and then a clock of 1 Hertz through A1, and finally a clock of 10 Hertz through A2. So let's turn on. Now, as you'll see, I've already done this before, and the interesting thing is because I have not reset it, it will it should continue to push until I've stopped resetting it. Until I have reset it. So you may, in this case I turned off the power supply, but another solution would be to unplug the reset and plug it back in. Again, for safety reasons, it would be better to build in a reset button if you're going to do that. Okay, so we've reset things. Now, if we run our Scopy, I'm going to return to the main view for the lab. And we will now run it. As you can see, we've created something very similar to the Corsair fans. A simple loop. It looks almost like the game of Snake, where every time he hits his tail, he deletes or eats himself. And you can play around with the speed of this, but essentially what I expect students to do as they do this lab is observe the INE file that we have and understand why the LEDs are being pushed the way they are, and understand how this pattern can be modified to improve the animation or create their own. So for instance, and I might be helping a little too much, but this is a more, this looks a lot better in my opinion. But you can do tons of other things, and I want students to give me 3 examples of changes that they've made to create a fun and unique pattern. So, for instance, you could set the clock A to be random and show me exactly what happens. So, you can create fun little animations with this tool, but the important part here is the exploratory aspect and the analysis. So as I said, we are limited by our options, but students in the lab document, I want them to explore using a latch so that we can output single things without having to go through the process of animation. I want them to explore, if they want, this is an optional one, explore the idea of Arduinos and whether or not they could, say, send a stream of bits to create a symbol. So I hope you enjoy the lab. More information is on the lab handout and what you should be investigating. But again, give me 3 different animations or symbols that you can generate using this method. Thank you and have fun.